Okay, so I'm going to talk about the binary instrumental variable model. This is joint work with Jamie Robbins. I subtitled it The Case of the Missing 9 Dimensions. And this directly builds on a very detailed discussion in chapter 8 of Judea's book that is basically where I first encountered this model. So I'm going to talk about the binary instrumental variable potential outcomes model. That's a causal model. I'll give you a formal description of the model, and I'll talk about Bayesian analysis and partial identification and some difficulties that arise and possible solutions. And then while we're going through it, I'll give you two quick examples. One is lipid data that's discussed in Judea's book, and the other is a different data set, flu data set. So here's the model, and the model is a graph like this. Z represents all three variables, Z, X, and Y are binary. Z represents some randomization into a control group or to a treatment group. And then X represents the treatment actually received. So this is a model designed to deal with the situation in which we ask patients to take a particular treatment, but they might not necessarily comply. They might choose to do something different. And then Y then is the final outcome. And the reason why this is a good model to think about, so the model includes the assumption that Z has no effect on Y except through X. And that's formalized here in the sense that there's no edge from Z to Y, and equivalently the structural equation for Y is a function just of an error term for Y and X. So Z comes in, but only through the value of X that we receive. And this is a good sort of test case in some sense to think about, because we can think about two extremes. The case where everyone complies, this is just a perfect randomized experiment. And in the case where people just completely ignore their assignment, we've got complete confounding. And so we can sort of see it as often in statistics, as a sharp dichotomy drawn between randomized experiments and sort of observational studies with confounding. This represents a way of having a gradual transition from one to the other. Okay, so X is a function of this type Tx together with Z. Y is a function of Ty together with X. And I'm going to give names. I'll give specific names to values for Tx. So someone who always takes the value X equals 1 regardless of Z, we call an always taker. Someone who always gets the value 0 regardless of whether Z is 0 or 1, we call a never taker. Someone who does as they're told is a complier, and someone who does exactly the opposite, contrarian, is a defier. Okay? Similarly, we have names for Y. Someone who takes value 1 regardless of their X value is always recover. 0 is never recover. Someone who recovers if they have X equals 1 and dies if they get X equals 0, we say is helped, and the opposite is hurt. Okay, so here's another way of thinking about this particular, the data that we have. We can think about it just as a contingency table with some sort of slight structure on it, where we get to see the margins. So this is, for example, the probability that X is equal to 0 and Y is equal to 0 given that Z is equal to 1. Okay, so given a large enough study, we get to learn, randomized study where Z is randomized, we get to learn the margins of this table, but we're interested in the internal cells. Okay? And so there are certain combinations that are impossible. For example, these are impossible, and that's a consequence of our exclusion restriction. We also see, I'm going to flip through this, but you can also see these two terms only show up, they both show up here, and this is the only cell that they show up in, and that will have important consequences. What are we interested in? We're interested in the average causal effect of X on Y, which you could think of as the proportion helped minus the proportion hurt. That lives in -1 to 1. You could think of that as the difference in percent recovering if everyone's treated versus if no one is treated. We may also look at, Tx had these names, always taker, never taker, complier, defier. Sometimes we might be interested in looking at the average causal effect amongst compliers or amongst defiers and so on. Here's this data set that was originally considered by Efron and Feldman relating to this cholestyramine drug. It was compliance was dichotomized by Judea, I believe. And the key point about this data set is that if you were in the control arm, you had no way of getting the drug. If you were in the treatment arm, you might choose not to take the drug. So you could have z equals 1, but x equals 0. But if you were assigned to be in the control group, there was nobody kind of going out and bribing the pharmaceutical company or the research lab to get hold of the drug. So z equals 1 implied x equals 0. And that simplifies the analysis in certain respects. So, so the natural thing to do, the model is not identified, and the natural thing to do is to try to find bounds on the average causal effect of x on y. So basically we say, given our observed margins, what are the possible values for the average causal effect? And so some earlier work came up with these natural bounds. Earlier work due to Mansky and Robbins came up with these natural bounds. These bounds, however, are not optimal if there are defiers. And Judea and Alexander Balke were the first to find analytic bounds in the general case using computational algebra methods. OK, so here's the lipid data. Here's the average causal effect of x on y. And I'm just giving you two numbers, which are the upper and lower bounds, the average causal effect of x on y. Okay, that's just treating the empirical distribution as if it were the population distribution. The obvious point is, well, we had 300 observations, 300 or so observations, but what about sampling variability? So, well, sort of standard way to approach this would be to put down a prior on those types, and then to go through, use Markov chain Monte Carlo, crank the handle, and generate posterior distributions. And in fact, that approach is carried out by Judea and also with Max Chickering. So we're going to do that for this particular example, but I'm going to do it for two different priors. Okay, so obviously, if you were a sort of tried and true Bayesian, you knew exactly what your prior was over these types. There's no problem at all. You just go through and crank the handle, you get your posterior. But often, sort of people don't necessarily have direct access to their priors. So we're going to look at what happens if we change the prior a little bit. So I'm going to consider two priors, one of which is just Dirichlet 1/8, 1/8, 1/8 on those 8 states. And then the other one is almost exactly the same, but I'm going to move 1/16 from the last state to the third from last state. Okay? Why have I got 1/8, 1/8, 1/8, 1/8? Well, that's because one of my colleagues who's a Bayesian said, well, you should try unit information prior. But we can ask the question of whose unit of information, but this was the proposal. So I want you to bear in mind the sample size for this lipid data was 337. The smallest count of the non-zero counts was 12. Okay? And I'm moving 1/8 of a person from one category to another in the prior. So here's what happens. These green curves represent prior draws for the average causal effect. Okay? So the solid line is the 1/8, 1/8, 1/8, 1/8. And the dotted line is what happens when we move 1/16 from the last 1/16 of the mass from the last to the third from last thing. Over here we can see this is the posterior. This is the posterior under the 1/8, 1/8, 1/8, 1/8 prior. And then this is the posterior as a consequence of moving that 1/16. Okay? So we've had there's been a big shift basically. This is the median under the symmetric one, and this is the median under the prior after we've moved 1/16 from an observation. Okay, so what's happened? What's happened here? This is surprising, right? Because if you think about it in terms of effective sample size, we've moved a tiny bit of mass. We've got 300 observations, and we've got a big change in the posterior. Okay, so this naturally raises the questions, well, why is that so sensitive? Why is the posterior so sensitive? A sort of deep question is, well, supposing somebody else does an analysis like this and they then present the posterior to you, well, what conclusion should you draw if presented with the result of such an analysis? Third question is sort of, is there a way to sort of finesse this problem? So let me do it. This is a very simple analogy that's much simpler than the instrumental variable case that I just talked about. Imagine we've just got two variables, a randomized experiment with x and y. Okay, and suppose that we want to find the average effect delta of x on y in a target population containing some known proportion of males and females. Okay? And the researcher the researcher reports priors on the model parameters and then gives you a posteriori over this quantity of interest delta. And the researcher says, I'm aware of partial identification, but look, here's my prior, here's my posterior. My posterior is clearly different from my prior. It's been informed by data. Be happy and take away my posterior and sort of regard that as being a summary of the inference that should be taken. So given this setup, suppose that later you subsequently learn an extra piece of information, which is you learn that the sample contained no females whatsoever. Right? There were just no females. Okay. So under those circumstances, most of us, I think, would say, well, that's great. Okay, so it's good that we know that there are no females. Please can you summarize what you've learned from the experiment about males, and then just keep your prior on the table about females, and we can have a separate discussion about your prior over females. Okay? Let's keep those two things separate. Don't mix them together. If you mix them together, the prior over males, as long as we've got a reasonable sample size, I don't have to worry about it too much. But the prior over females, it's not going to be changed. Okay? So I'm running out of time here, but basically what I propose is a reparameterization. So the problem that's arising is that our observed data lives in a 6-dimensional space. The model that we've got over the counterfactual, over the potential outcomes, lives in a 15-dimensional space. So 9 dimensions disappeared somewhere. Okay? It's a little bit like string theory. Okay? And so what I propose is I propose a reparameterization. So I'm going to reparameterize into 2 parameters, a parameter theta of dimension 6 that will be completely identifiable from the observed margin, and a parameter aleph of dimension 9 that is completely unidentifiable. It's completely independent of z, x, and y. Okay? And basically, you better get to know your prior over aleph because it's going to be with you forever. It's never going to be changed by the data. Okay, so I'm sufficiently out of time. I'll just show you how this works with the lipid data. So for the lipid data, basically, in that case, because we had no defiers or always takers, things are simpler. The observed data lives in a 4-dimensional space, and we only have 8 types. So there are, in this particular case, there are only 3 missing dimensions. One of the missing dimensions can be thought of as the effect of the drug on never takers. And then there are 2 other parameters that are associated with the proportion of helped, hurt, always recover, and never recover amongst never takers and compliers. And those are irrelevant for the ACE, those last 2 parameters. So we've basically got one unidentified parameter, and it's completely disconnected from the data. So in a certain sense, we could do a Bayesian sensitivity analysis whereby we just say, well, you tell me, what do you think is the probability of recovery for never takers if they were to receive the drug? And you can choose some value of that between 0 and 1. And the average causal effect of x and y is on this axis. And depending on which value you choose, you'll get a point on this line, which is the maximum likelihood estimate for the average causal effect, given the value that you pick. And these lines here are the bounds that we saw earlier. And then we can then do a Bayesian analysis. And this is giving a 95% posterior credible interval. And this is a simultaneous 95% posterior credible interval. So this parameter about which there's no information in the data whatsoever, you can come along. And if you happen to think that it should be there, you can then look at, well, this is what I then believe about the average causal effect. If I think it should be down here, then I will draw my conclusion here. Harder case, so this was an easy case with no defiers or always takers. The harder case is where there are defiers or always takers. I'll just show you this graph. This is a graph describing how those 9 dimensions get hidden, basically. So there are basically there's 1 dimension associated with things over here, 1 dimension associated with compliance types, and one dimension over here, and then there are 4 other dimensions that are irrelevant for the average causal effect. And then there are 2 parameters, again, that are completely disconnected. This is the effect of treatment, the effect of not taking a treatment on always takers, and the effect of taking a treatment on never takers, like the parameter we saw before. So here's a flu data set. Notice there are no zeros here. So this is with a flu vaccine. People's doctors were randomly assigned to encourage them to get a flu vaccine or not to get a flu vaccine. We get these counts. This was analyzed by Hirano. They had baseline covariates that we're ignoring here. And this is basically a description of the maximum likelihood estimate, which is a three-dimensional object, three-dimensional set of possible distributions that give rise to the observed empirical distribution. We can also do this. We can get bounds on. We can do sensitivity analysis and get bounds on average causal effects for always takers, compliers, defiers, and never takers. Here we can also do sensitivity analysis on bounds for the global average causal effect as a function of the distribution over compliance types, which again is something that's not identified but is bounded. Here are the bounds. Here are the I have 2 slides left. Here are the bounds that you'll get from the Bulky and Pearl analysis. Here are the natural bounds. They look exactly the same, but in this example, if we zoom in, we can see this is the Bulky and Pearl bounds that are tighter than the natural bounds. It's a very small difference, but they are tighter. Here's the summary. Yuda's work on bounds for the ACE and the general binary IV model opened up a whole new set of causal methods and analytic approaches. Care is needed. This isn't specific to the IV model, but care is needed when incorporating proper priors with partially identified models. And reparameterization to separate identified and unidentified parameters can be helpful in these situations.